Thank you so much for introduction. And I would like to also thank the organizer for providing such a nice workshop. I learned a lot about the fermions. And today I'm going to talk about the work that was recently concluded. It's basically quantum-enhanced interferometry with a squeeze light. The talks falls under the category of the quantum metrology, quantum optics, spectroscopy, and microscopy. So the basic idea is that we ask ourselves, is it possible to improve the precision of multiphoton absorption measurements by using non-classical sources of the light, which is for us is a squeeze light. The problem is that when you're using a classical light in order to do something like a multiphoton absorption, there is a cap on the level of the precision that you can get. And there has been this idea going around that maybe if we use quantum states of the light, we would have a better precision. In upcoming slides, I'm going to convey 3 key messages, and I hope that it would be your take-out messages. The first one is that, yes, indeed, we are going to get a significant improvement if we use a squeezed light or some sort of the quantum light to do multiphoton cross-section estimation. I'm going to show you that this enhancement is going to be robust against certain experimental errors and problems. And I'm going to also show you that in order to achieve this enhancement, the platform that we need is something that is called nonlinear interferometers. So first, I'm going to actually introduce all of this terminology that you are seeing here, and it might not be familiar for you. Then I'm going to give you a peek to the setup that we have considered, and then up to the result. So let's start with multiphoton absorption. So basically, it is when a sample absorbs several photons simultaneously and goes from the ground state to the excited state. The sample can absorb photons with different frequency, but here we consider that it is absorbing only identical photons. So basically, we have some single mode light field. Multiphoton absorption processes is almost as old as quantum mechanics. They were initially introduced in the 1930s, and then they were realized experimentally after the invention of the laser. So why do we care about multiphoton absorption processes? They have a specific feature that are very interesting. The first one is large penetration depths. So what does it mean? Imagine that you have some kind of a complex material, and it is made out of several layers, and you want to try to understand what is happening inside the matter. So you need to be able to go deep into the matter, and this is where the multiphoton absorption processes come in. Then there is a nonlinear dependency on the profile of the beam. This is very important, especially if you might somehow trigger different kinds of phenomena inside the matter by shining the laser on it. This helps you to somehow distinguish photons from different phenomena. And then you have this suppression of the single photon diffraction limit, and it also enables you to go from to improve your resolution from optical microscopy to molecular scales. Because of these features, these type of processes have been widely used for imaging biological material. They were used for chemistry and also in different parts of the physics. But despite having this amount of application, we have one big problem with them. They're weak. They're really, really very weak. And consequently, the signals that they are producing is also very bad, and you'll not be able to really get something substantial. So how do we circumvent this problem? There's one straightforward way, is just using some kind of ultra fast, strong laser field. But if you're working with some kind of a photosensitive material, this is a very bad solution, because you might actually photo damage the material or photo bleaching. So this is not the way to go with. So the second solution, which we actually are following, is just keep the intensity of your laser field at the same, but try to reduce the noise level that is inside your light field. And this can be done only with quantum states of the light or squeezed light that we are going to use. So what is a squeezed light? Well, in a nutshell, it's a light field that has a reduced statistical noise in one of its quantum parameters. So the basic idea here is we actually invoke Heisenberg uncertainty principle and try to reduce the uncertainty in one of the parameters at the expense of its conjugating parameter. So let me show you how does it visually look like. So this is a Wigner function diagram for the P and Q. P and Q is actually called quadrature operators for the light field. And if you take a look at it, then you see that the uncertainty of the P and Q is identical. Now, we have the possibility to actually squeeze these Wigner function diagrams, whether in the P direction or in Q direction or in both of these directions. Let's say that we are squeezing it in the Q direction. What happens? We have a new uncertainty for the Q and new uncertainty for P. And if we compare them, we'll see that we have a lower uncertainty in this squeezed state of the light. So, and because of this lower uncertainty, this kind of light field has been used for precise measurements, such as phase estimation, small displacement measurements, or maybe the most famous application of the squeezed light is detection of the gravitational waves. But how do we produce them? We actually use a process that is called down conversion. So the idea here, you have some kind of a nonlinear crystal, you pump it with a laser field, and what happens is that some kind of a nonlinear process is triggered, and each of your photons from your pump field is converted to 2 photons with a smaller frequency. This is nice, but we just don't need, this is not enough to have some kind of a squeeze light and shine it at the sample. We need to have some kind of a platform where we can actually actively engineer the light field. And this platform is something called nonlinear interferometer. So what is nonlinear interferometer? I need to take a step back and talk about linear interferometer. This is also important because I'm going to compare the result between a nonlinear interferometer and linear interferometer. So the linear interferometer is the usual Mach-Zehnder interferometer, which is made out of the 2 beam splitter. So the idea here is that the laser field comes in and it is goes through the beam splitter, and it is split into 2 directions. In one of these directions, we have a sample, and the light field interacts with it. In the other one, we don't have any sample. And then in the second beam splitter, these 2 light fields are recombined again, and some kind of interference pattern start to form, and that is what we are actually detecting. Nonlinear interferometer, which is also called SU11 interferometer, is basically the same, but instead of having the beam splitter, we have nonlinear crystal. The presence of this nonlinear crystal makes a big differences. The reason is because beam splitter and linear interferometers, they are basically some passive objects. They don't change the properties of the light field. The only thing that they do basically is just change the direction of the light field. Whereas in the nonlinear interferometer, these nonlinear crystals can actively change the properties of the light field. They can actually create entanglement or change the entanglement and so on. So we had all of the introduction that we needed. Now let's go to the setup. So the setup that we have considered looks like this. So we have an initial state of the light, which we consider to be seeded. Then we have the first nonlinear crystal that performs the first squeezing for us. Then we have our multiphoton absorption material. The squeezed light comes in and interacts with it. And then we have our second squeezing procedure. And afterwards, we have the detection. Oh, I jumped. In order to make things as realistic as is possible, we need to consider that there might be some kind of experimental errors that is happening in this setup. So we introduced 2 sets of errors. One is inside the interferometer, and the other one is outside the interferometer. The one that is inside the interferometer is basically like when you have some kind of scattering of the light by the sample, or some kind of unwanted processes that might be triggered. Outside the interferometer, these sources of error can be when you have some kind of a faulty detecting devices that does not register the photons properly and does not detect it. Okay? Well, How do we model all of these stuffs? The seeding is actually modeled by some kind of a displacement operator, which gives us this laser field. Then the squeezing is actually modeled by Bogoliubov transformation. For the multi-photon absorption sample, we use the Markovian Limbaugh master equation. So basically, we consider the whole system to be some kind of an open system. We form the density matrix and try to solve everything. The single photon losses or the sources of the error that I talked about here, we consider them to be single photon losses, and we model them with beam splitter transformation, which is a usual practice in the field. And we need an observable at the end to make a measurement, and we use this photon number measurement, which is basically somehow related to the intensity measurement. And we need some kind of a quantity that quantifies how much improvement did we have if we use the nonlinear interferometer compared to the linear interferometer. We use a quantity that is called sensitivity. It is actually modeled via error propagation method. Well, this is a theory work, and I'm supposed, yeah.
No, I'm just curious. So, like, in my understanding, when you have squeezing things, you look on the face of this operator in dynamics to make some measurements. So, like, why here we use this photon number as an observable?
So basically, you can actually, we are not checking whether the phase of the matter is going to be changed. What we are doing is, it goes back to this multi-photon absorption process in this Limbaughian. So what we do is actually somehow form a density matrix that contains all of the information about the material part and the laser part, the light field part. And then we trace out the material part, and we take a look at the light field only. And this has some kind of imprinted information inside this Limbaughian equation that gives you about some information about the cross-section. Yes, because if I go to this slide, so yeah, it's a theory work. I need to show you some formulas. So this is the whole thing, how it looks like, all of these modeling. You don't need to worry about any of these formulas, and you're not going to see them. The only one that I want you to concentrate is the last one. So in order to have the sensitivity, I look at something that is called the absorbance. I take a look at the uncertainty of the absorbance, and this absorbance is actually linearly related to the cross-section. Here, sigma is the cross-section of the process, and is the density of the number of the molecules, and L is the length of the sample. So let me get a little bit into the sensitivity, because this is where we are actually making the calculation. So sensitivity is basically uncertainty in measuring a quantity, which for us is the absorbance. So I cannot measure absorbance directly. I need some kind of observable, and our observable have the information about the absorbance. So if I want to understand what is sensitivity, is basically this uncertainty for this absorbance, and it is somehow some kind of a small relation about variance of that observable and somehow changes of that observable with respect to that observance. Okay, so I explained enough for this stuff. So remember, the goal is actually to improve the sensitivity. And how do we improve the precision? How do we improve it? By optimizing the sensitivity. And the optimization of sensitivity means we need to look at the situation where we minimize the sensitivity or this uncertainty that I showed you. So I need to do 4 specific things. I need to optimize my parameters. I need to characterize my light fields. And I also need to identify the parameter regimes. And I need to scrutinize everything by looking at the effects of the internal and external loss on the behavior of the enhancement. So let's go to the last part, results and optimization. So the first thing that I need to specify is what type of processes should happen in this nonlinear crystal. So here we have this 3D schematic behavior. So this sphere is actually the light field. And I'm going to actually plot everything for the 2-photon absorption. So what I do is, this is the Wigner function diagrams in order to make everything visually more understandable. So I prepare some kind of a seeded state. My light field passes through the first nonlinear crystal. And in this first nonlinear crystal, what we need to do is squeezing in the direction of the P quadrature. This is called actually amplitude squeezing. And what you do is basically try to reduce noise in the amplitude of your light field. Then my light field passes through the sample, and it creates these non-trivial patterns in the Wigner function, the positive and negative Wigner function. And then my light field needs to pass through the second crystal. And what we do in the second crystal is basically reverse what was done in the first crystal. So we anti-amplitude squeeze the light field and try to somehow squeeze it more than what was done in the first crystal. So what we do, first amplitude squeeze and then anti-amplitude squeeze. Okay, this is the processes that we need. In the next step, I need to talk to you and tell you about the parameters and how we need to somehow design the degree of squeezing. This is very technical. I'm not going to get to it. So let's just say that I have already did this optimization for this degree of squeezing. Now, let me compare the linear interferometer with a nonlinear interferometer. The dashed lines are the linear interferometer. The solid lines are the nonlinear interferometer. So the first thing, I take a look at the optimized sensitivity. And if you take a look at it, for example, let's say I have, I actually make every contrast with respect to the photon number of the photons that are reached in the sample. This is because I don't want to compare apple and oranges together. So let's say that I have 100 photons, and I'm looking at the 2 photon absorption processes, where m is equal to 2. And the sensitivity that I can get for SU11 interferometer is much smaller than the linear interferometer. So this is a proof that we have indeed a significant enhancement. But how big is this significant enhancement? I'm looking at the scaling behavior of the optimized sensitivity with respect to the number of photons that are reaching the sample. And you can see that for the coherent or linear interferometer, we have such a relationship. M is actually order of the process. If you put m equal to 2, it's 2 photon absorption process, 3 photon absorption process. And you can see that they have these differences in their power. So let's say if you have 100 photons, if you have 100 photons, SU11 interferometer is actually have 1 order of magnitudes better sensitivity compared to the coherent interferometer. Yes?
What is the Planck constant in this, effective Planck constant in this model? So like in which units you measure your variance?
This is somehow unitless, but you can actually somehow...
I think it's the initial, whatever you start with, right? You can't do better than...
Yeah, exactly. You basically you have this kind of a Heisenberg uncertainty, and from there you have some kind of a limits on the how much you can actually make things smaller or bigger. And from there, you can actually put the Planck constant equal to 1, or no.
My question is more like, so in typically there is like the standard quantum limit, and then like using some squeezing or entanglement state, you can go beyond this limit. So like,
yeah, but there's actually some kind of a, so if I want to talk about the really hierarchy of the limits, you have something called Fisher information. Yeah. And then Fisher information is actually put down the highest limit. And from there, you cannot actually go beyond this limit. And this Fisher information can actually go to the Heisenberg limit. And from Heisenberg limit, Heisenberg limit is actually the best limit that you have.
How like the unit is using this squeezed light improve the sensitivity in your case?
So this is exactly what I'm showing here. Look, for example, it is optimized sensitivity. For a classical light field, if you have 100 photons, the sensitivity that you can actually get is this. This is the best sensitivity that you can get. Whereas for the squeezed light, your sensitivity is much smaller. And it is actually can be 1 order of magnitude smaller. So this is, especially if you're working with the photosensitive material, this wonder of order of magnitude can somehow photobleach your sample, photodamage your sample or not. So if I go, for example, to absorbance, which basically gives me this idea that how many photons do I need in order to get the signal for a specific process, you can see that, for example, if you have, if your signal that you are looking for is, let's say, 10 with the power of, 5, which is here, and for the SU11 interferometer, you have much, much lower photon numbers in order to get the signal for comparing to the classical light field. Okay? So I also need to take a look at the effects of the external and internal loss, these experimental errors. Interestingly, for SU11 interferometer, the external loss has absolutely no effect on the sensitivity. This means that if you have some kind of a faulty detecting devices, it's not going to somehow change the sensitivity of the measurement that you have. Whereas for the linear interferometer or the classical light, you see that it is starting to degrade. Now, I need to also take a look at the internal loss. Unfortunately, SU11 interferometer or squeezed light cannot completely erode the effects of the internal loss. And you can see as we actually have a higher level of internal loss, the superior scaling behavior of the SU11 interferometer start to decline. And at some point, it would actually become equal to the ideal linear interferometer. I should say that this is just a comparison between the scaling behavior. In reality, SU11 interferometer or a squeezed light is going to always outperform the classical light under any circumstances, but with our optimization. Okay, this brings me to the summary. So I showed you that, yes, indeed, we had some kind of enhancement if we use SU11 interferometer, and this enhancement was coming because we have these non-classical sources of the light, and we had this robustness of the enhancement against certain experimental imperfection. And this enhancement was due to using nonlinear interferometer and also a squeezed state of the light. At the end, I would like to acknowledge my collaborator, Maria Chechova from Max Planck Institute of Erlangen, Carlos Munoz from University of Madrid, and Frank Schnabin, which was the main PI, and he's also from my supervisor in Hamburg University. Thank you so much.
Thank you very much, Shahram. We have time for quite a few questions, so let me start with one. What sets that scale M